let's look at this diagram and see if we really understand this. I am going to put a alternating current source here that's going to go high, it's going to go low, but it's going to cross zero a lot. So that is going to induce what in this around it? It is going to produce exactly magnetic fields around it. The AC current will induce magnetic field, and those magnetic fields, we have to remember is that, yes, we know that it induces a magnetic field, but it doesn't just arrive out of nowhere. We have to remember that it grows and it shrinks. It's a growing magnetic field and it's a shrinking magnetic field, and it's a growing magnetic field and it is a shrinking magnetic field. And it's going to grow, then it's going to shrink down to zero, then it's going to change direction and grow again, and then shrink down to zero according to that current. So it is at zero. Oh, bad symbol for zero because it looks like flux. Then it grows, and then, excuse me, it goes back to zero. And then, wait a second, it grows, it peaks, and then it shrinks, and then it goes back to zero. And then it grows in opposite direction. And then it peaks in that direction. So it was growing like this. And then once we get to the other side of the sinusoid, it goes like this. And then it grows like this, peaks and shrinks in the same direction. When it shrinks, it's the same direction, okay? Grows in the opposite direction, it peaks, it shrinks, then it goes to zero, and then that process repeats itself, okay? So these are growing and shrinking, which I can draw like this. They're growing and shrinking. They're going this way, then they're going this way. Now, that is going to produce eddy currents. And as we know, the eddy currents are induced by, and we don't have a nice symbol for eddy currents. Maybe we can make up our own. Maybe we can go like this. Maybe we can go like a script E for eddy. Induced by the magnetic flux. And that means that they are perpendicular to the flux. And what else do I have to know about eddy currents? They are only on conductive material. So it's very important to know that true or false, are there eddy currents up here? True or false, are there eddy currents here? True or false, are there eddy currents here? There are not eddy currents here. It's in free space. There are not eddy currents here. It's in free space. There are, yes, eddy currents here, perpendicular to the magnetic field, and yes, in a conductive material. So induced by the flux, perpendicular to the flux, only in the conductive material, and they grow, peak, shrink, change direction. They grow, peak, shrink, hit zero, change direction, grow, peak, etc., just like up here. And they do so perpendicular to the flux. Now, if I set this current at zero, I'm going to do that over here, then therefore flux will be nothing. Therefore, eddy currents, I made up that symbol, will be nothing. Okay? Good. One more thing to remember, just one more thing. if I set my current equals constant, then my flux will be constant. What do we mean by constant? It is X number of Webers per meter squared. There is a flux density and it stays the same. It'll be constant. Therefore, eddy current is not constant. Well, actually, it is constant. It is absolutely nothing. No eddy currents. When do we have constant current? It is DC. That's a DC case. When do we have constant flux? That's a DC case. DC case. When do we have no eddy currents? That's a DC case. Oops. That is also a DC case. So eddy currents are a problem with AC circuits, not DC circuits. And that is very important to remember. This is a DC case. In AC, yes, we are going to be crossing the zero, but the flux is still changing. It is still, it has been going down and it'll still go down more. It's been going up, it'll still go up more. So it is a changing flux case. So we are still inducing those eddy currents. And we have to remember that eddy currents are not good because they create heat. That's another thing to remember about eddy currents.